Okay, so this is going to be part two of heat and thermodynamics. So specifically, we're going to be focusing on specific heat. So we'll cover that in a second. So specific heat, what is specific heat? So the specific heat is the amount of energy it takes to move a substance temperature up or down 1 degree Celsius or 1 Kelvin. So let me give you an example. So if I was to heat water from 0 degrees to 1 degree Celsius, then I would need a certain amount of energy. And we know that energy for water is 4.18 joules. So, specifically 1 gram of water. That's how much energy I would need to heat 1 gram. If it was 2 grams, it would be double the amount. So, here's the specific heat formula where Q is going to be in joules, the amount of heat or energy I'm going to need. C is the specific heat. So if it was water, it would be 4.18. M would be the mass in grams because specific heat is joules over grams. And then delta T, delta always stands for change, so it would be change in temperature. So it's your final temperature minus your initial temperature. And specific heat of water, we're just going to be using this a lot. So write this in your notebook, commit it to memory, specifically the water one. But ice and steam are actually 2.01, so they're actually a little bit less. It doesn't take as much energy to change the temperature of ice or the temperature of steam, but it takes more than double the amount of energy to change the temperature of water, which is why it feels like hot water just doesn't like to cool down. So let's see. And another piece of information is if I calculate that my Q or my energy that I got is positive, it's an endothermic reaction. That means energy was absorbed into the system. So the system is going to be taking in energy. And if my Q is negative, that's an exothermic reaction or a reaction where energy has left the system. Okay, so let's talk a little bit more about endothermic and exothermic because that's important. So if I look at this graph here, whereas the x-axis is time, like it normally is, and the y-axis is the amount of energy. So I have this thing called activation energy. That's the energy needed for the reaction to start. And then if my energy at the end of the reaction is higher than my energy at the beginning of the reaction in the system, I've gained more energy. I've absorbed energy in the reaction, right? So that would be endothermic. And usually, endothermic reactions, well, not usually, all the time, endothermic reactions feel cold. They don't, mainly because it's taking energy out of the environment and storing it in chemical bonds. So, any type of endothermic reaction would feel cold to an observer. An exothermic reaction is the exact opposite. So here I have an energy level of a system. It activates, it requires a certain amount of energy to start. And then the reaction happens. And then I see at the end of the reaction, my level of energy is a lot lower than where it is where it started. So this would be considered an exothermic reaction. Energy left the system. So this would be any type of reaction that we feel that is being hot. Okay, let's finally use the equation and practice with it. So to what temperature will a 50-gram piece of glass raise if it absorbs 5275 joules of heat and its specific heat capacity is 0.50 joules per gram times degrees Celsius. So don't worry about all the units right here. They all kind of cancel out as they go. This is just specific heat, so that is my C in the equation. And then my initial temperature is 20 degrees Celsius. So this seems kind of tricky because it gives me my Q. I'm not solving for Q. I'm actually solving for my final temperature, right? So when my delta T, if I go with delta T, let me go ahead and, oh, I solved the whole equation for you. Oh, well. So if I look at my delta T, that's the change in temperature. So that's my final temperature minus my initial temperature. So once we plug all this in, the energy for the whole reaction goes where Q goes. So 5275. And then I've got my M, or my mass, which was 50 grams. And then I've got my specific heat, which was also given to me, 0.50. Okay, so that stacks up pretty nicely. And then I have to kind of break down delta T because I'm solving for something within delta T. I'm solving for final temperature. So that becomes a little bit more complicated, but not too much more. It's still a very simple algebraic equation. So I plug all this stuff in, and then my step 3 would be to simplify. So 50 times 0.5 equals 25. I distribute to both sides of this subtraction equation on the other side of the parentheses. So 25 times final temperature, and then 25 times negative 20 would be negative 500. So I've got 5275 equals 25T minus 500. So then I can redistribute over here. I could add 500 on both sides. That's what I've done here to get rid of my 500 on this side. And then I divide both sides by 25. And this is just me doing it all in one step. So 5275 plus 500, divide that by 25. I get a final temperature of 231 degrees Celsius. Okay, one more. So this is you're practicing on your own. This one should be a little bit simpler, simply because you're looking for the energy. So you're looking for Q. You don't have to rearrange anything. You're just plugging numbers in. So I have 100 milliliters, which is the same thing as grams. So 100 grams of water. It's 4 degrees Celsius. It is heated to a temperature that is 37 degrees Celsius. So you need to find the change in temperature there. It should be a positive change, so it should be a positive number. If the specific heat of water is 4.18, calculate the amount of heat energy needed to cause the rise in temperature. So you're calculating for Q. So go ahead and pause the video and see if you can solve for the answer. Okay, the answer is 13,794 joules. I'm going to go ahead and be looking for that in your notebook during the next notebook check to see if you showed your work. But here's the answer just to make sure that you did it correctly. And I will see you next week when we start going over calorimetry.